In the last module, we have discussed sign test, defined sign test statistic, and given some properties. In this module, we shall provide the unbiasedness property of sign test, large sample distribution of sign test, and hence a large sample test, and find a confidence interval for the location parameter using the cutoff points of the sign test. We also obtain the sample size required to attain a fixed power level. Finally, we give an application of sign test, namely the Cox-Stuart test of trend. So, we have discussed sign test statistic. There are some properties, symmetry and consistency. Now, we shall start with unbiasedness and end up with some applications of sign test. Now, we shall start with unbiasedness of sign test. Consider testing theta equal to theta naught against theta greater than theta naught. Then the power function can be expressed as probability s theta naught greater than s alpha under theta plus a probability s theta naught equal to s alpha under theta. Since probability under theta s theta naught equal to s alpha is nothing but the difference probability s theta naught greater than s alpha under theta minus probability s theta naught greater than s alpha minus 1 under theta. Power function can be expressed as a probability s theta naught greater than s alpha minus 1 plus 1 minus a probability s theta naught greater than s alpha, where both the probabilities are evaluated under theta. Now, s theta naught is expected to be larger under theta than under theta naught. Thus, s theta naught under theta is stochastically larger than s theta naught under theta naught. Then, under any theta, probability under theta s theta naught greater than k greater than equal to probability s theta naught greater than k under theta naught. Using these, we find that expected value of phi naught, that is power function, exceeds probability s theta naught greater than s alpha plus a probability s theta naught equal to s alpha, where both the probabilities are evaluated under theta naught. Then the right hand side of the above is nothing but expected value of phi naught under theta naught, which is again nothing but alpha. Thus, we find that expected value of phi naught, that is power function, exceeds alpha for any theta greater than equal to theta naught, and hence unbiasedness follows. Thus, correct decision is expected to be more frequent than the wrong decision. Similarly, unbiasedness for the other tests can be proved. Now, following any hypothesis testing procedure, the objective is to derive a confidence interval. In parametric inference, confidence interval is often obtained by inverting the acceptance region. In sign test, we also follow the same procedure to obtain a confidence interval for the median theta. Thus, we can use the cutoffs of sign test to get a confidence interval of theta with confidence coefficient at least 1 minus alpha. Consider the acceptance region of the non-randomized level alpha sign test for theta equal to 0 against theta not equal to 0. Then the acceptance region can be expressed as C less than equal to S0 less than equal to n minus C, where C is such that probability C less than equal to S0 less than equal to n minus C greater than equal to 1 minus alpha under H0. Observe that as we increase theta, the number of observations exceeding theta decreases or does not increase at least. Thus, S theta is non-increasing in theta. Now, from the definition of order statistics, we know that for any k, x ordered r less than k, if and only if at least r observations are less than k. Now, consider the inequality s theta less than equal to n minus c, or equivalently n minus s theta greater than equal to c. That is, the number of observations less than theta is at least c. Hence, we get the inequality x ordered c less than theta. Similarly, we get S theta greater than equal to C is equivalent to theta less than x ordered n minus C plus 1. Thus, C less than equal to S theta less than equal to n minus C is equivalent to x ordered C less than equal to theta less than x ordered n minus C plus 1. Then, the probability that the random interval x ordered C, x ordered n minus C plus 1 covers theta is equal to probability C less than equal to S theta less than equal to n minus C evaluated under theta. Since the distribution of S theta under theta is the same as the distribution of S0 under H0, we have probability under theta C less than equal to S theta less than equal to n minus C equal to probability under H0 C less than equal to S0 less than equal to n minus C. Since the test is of level alpha, the right hand side probability above is at least 1 minus alpha. Thus, the coverage probability of the random interval x ordered C, x ordered n minus C plus 1 is at least 1 minus alpha. Hence, the random interval x ordered C, x ordered n minus C plus 1 is a confidence interval for theta with confidence probability at least 1 minus alpha. Next, we shall discuss how to perform sign test in large samples. Note that under the null hypothesis, S has a binomial distribution with parameters n and half. Then, by de Moivre-Laplace limit theorem, the new variable S star, which is nothing but S minus n by 2 whole thing divided by square root of n by 4 is asymptotically normal 0, 1. Therefore, different tests can be performed in large samples using S star. For example, consider testing theta equal to theta naught against theta greater than theta naught. Then, the corresponding large sample test is non-randomized and rejects the null hypothesis if the observed value of S star exceeds tau alpha, where tau alpha is the upper alpha percentage point of a standard normal distribution. Similarly, the large sample tests for the other hypothesis can also be constructed. So, we have discussed so far sign test for median. But sign test can also be applied for tests regarding quantiles other than the median. Suppose theta is the quantile of order p. Then sign test can still be used to test theta equal to theta naught against the usual alternatives. Properties like consistency and unbiasedness will be retained. However, the distribution of S theta naught in this case will be binomial with parameters n and 1 minus p under the null hypothesis. Naturally, the statistic for the large sample test will be S star equal to S minus np whole thing divided by square root of np into 1 minus p, which is asymptotically normal 0, 1 under the null hypothesis. Next, we consider sign test for paired data. Often, we have observations on the same experimental units. For example, suppose the data is available from a patient before and after a drug is administered. In such a case, we want to know whether there is any effect of drug on the patient. The main problem is that the observations within pairs are correlated. Formally, suppose xi, yi, I from 1 to n are random samples from a unknown continuous but bivariate distribution fxy. Then the null hypothesis is that x and y are exchangeable. That is, the distribution of xy is nothing but the distribution of y and x. Suppose the median of the distribution of difference z equal to x minus y is theta z. Then under h0 theta z equal to 0. Thus, the objective is to test the null hypothesis theta z equal to 0 against the usual one-sided and two-sided alternatives. Naturally, theta z equal to theta 1 indicates that x observations tend to be theta 1 units larger than the corresponding y observations. Thus, statements about theta z give information about the relative locations of the marginal distributions. Then the appropriate procedure is simply sign test based on the new sets of observations zi equal to xi minus yi, I equal to 1 up to n. Such a procedure based on the paired data is known as a paired sample sign test. Now, we shall discuss a somehow different thing. This is called determination of sample size. We shall discuss how sample size is an indicative measure of sensitivity of the test. Although the sample size determination can be related to any testing procedure, we discuss it in the context of a sign test. We need a random sample to perform a sign test. Suppose the objective is to determine a given shift in the median. Then consider testing h0 theta equal to 0 against the alternative theta equal to theta 1, which is positive for specified theta 1. Now, the test can be based on a small sample size or a large sample size. So, how many observations do we need? Often, the observations are subject to some cost and time constraint. Therefore, the experimenter needs to choose the sample size which will be sufficient to reach a decision. The usual technique is to determine n in such a way that the test has size alpha and power at the alternative 1 minus beta, where alpha and beta are specified in advance. Now, consider the non-randomized level alpha sign test for theta equal to theta 1, which rejects the null hypothesis if S exceeds K, where K is such that probability S greater than equal to K under H0 is less than equal to alpha. Since S has a binomial distribution with parameters n and success probability 0.5, the above condition reduces to summation I from 1 to K up to n choose I 0.5 whole to the power n less than equal to alpha. Then, if we define P equal to probability x1 greater than 0 under theta 1, then the power of the above test becomes summation I from K to n choose I P to the power I 1 minus P whole to the power n minus I. Then, we need to determine sample size n such that the conditions summation I from K to n choose I 0.5 whole to the power n less than equal to alpha and summation I from K to n choose I P to the power I into 1 minus P whole to the power n minus I greater than equal to 1 minus beta are satisfied simultaneously. This is naturally a complicated problem as n and k are both integer and are to be determined simultaneously. Moreover, the solutions are not unique. In practice, we fix nk, satisfying the level alpha criterion, and find the pairs satisfying the power requirement. A numerical example will be helpful to understand. Suppose alpha is set at 6% and power at 80%. Then, for n equal to 15, we get k equal to 11 satisfying the level alpha condition. Now, we set theta 1 equal to 0.8 and consider f as normal, Cauchy and logistic. For normal distribution, we get power as 0.801. But for the Cauchy distribution, we get 0.57 and for logistic distribution, we get 0.47 as the power. Thus, for normal population, the required sample size is 15. However, we need more samples to achieve 80% power for the other distributions. A similar exercise with alpha equal to 1% gives n equal to 25 and k equal to 18. Then, for normal distribution, we get power 0.851, but for the Cauchy distribution, it is 0.585 and for logistic distribution, it is 0.48, which supports the need of further observations. Thus, for distributions other than normal, the sample size becomes huge. For a clear picture, we use large sample approximations. We can get an easier formula using the large sample approximation. To be specific, consider testing theta equal to 0 against theta equal to theta 1 with specified theta 1. Then, the large sample test, as we have defined earlier, rejects the null hypothesis if S by N exceeds C, then the size and power requirements are probability under H naught S by N exceeding C equal to alpha and probability S by N exceeding C under H1 as 1 minus beta. If sigma I square is the asymptotic variance of square root of n S by N under Hi, then the above requirements can be equivalently expressed in terms of the standardized variables square root of n S by N minus 0.5 divided by sigma naught and square root of n multiplied by S by N minus P whole thing divided by sigma 1 as in the slide, so that large sample distributions of these variables can be used. Since the large sample distributions are normal, we get the approximate relations C minus 0.5 equal to tau alpha sigma naught divided by square root of n and C minus P equal to minus of tau beta sigma 1 whole thing divided by square root of n. Then a simple algebra gives the approximate sample size formula as given in the slide, where sigma naught square is nothing but 1 by 4 and sigma 1 square is nothing but p into 1 minus p. The same formula is valid for testing theta equal to 0 against theta equal to theta 1, where theta 1 is negative and is specified. For two-sided alternative, we need to replace tau alpha by 2. Thus, the approximate formula is a nonlinear function of p. Since p equal to 1 minus f of minus theta 1, we can examine the effect of different distributions on the sample size. For the purpose of comparison, we consider three distributions, namely normal, Cauchy and logistic. The median for each distribution is taken as theta and scale parameter unity. Then consider testing theta equal to 0 against theta greater than 0. For various choices of theta, we have computed the approximate sample size with alpha as 5% and power as 80%. The approximate sample size for different distributions and for different theta is plotted in the next page. The plot depicts the same fact as observed in the exact numerical study. Normal distribution takes the least number of samples to reach the desired power level among the candidates. Logistic distribution takes the highest number of observations to reach 80% power. In addition, as we increase theta, the required sample size decreases for each candidate. Now, sign test plays an important role in non-parametric inference. In many practical examples, sign test can be used. We shall give two such applications. First one is on a test of trend. For data coming from some production process, it is often desirable to check the presence of trend. That is, we are interested in knowing whether there is any time dependency among the observations. Suppose xi, I from 1 to n are IID observations from a continuous population f. The hypotheses for such tests are expressed as absence of trend in the data against presence of an upward trend. For the Cox-Stuart test of trend, assume that the observations are sequentially observed and x1, x2, xn are ordered as they are observed. Assume that n is even and define c equal to n by 2. However, if n is odd, the middlemost observation, that is the n plus 1 by 2th observation, is deleted. Then the whole set of observations are divided into xi, I from 1 to c and xi, I from c plus 1 up to small n. We club the observations into pairs xi, xi plus c, I from 1 to c. If an upward trend is present, then further observations are expected to be larger than the earlier observations. Thus, the event xi plus c exceeding xi is more probable than the event xi plus c less than xi for every I. If we set p equal to probability xi plus c greater than xi, then the testing problem can be expressed as h naught p equal to half against H1 p greater than half. Thus, the problem is nothing but that of the sign test. Naturally, the test statistic T is the number of pairs xi plus c I from 1 to c for which xi is less than xi plus c. Thus, T is the sum of the indicator functions of xi less than xi plus c. The test statistic is nothing but the sign test statistic based on the difference xi plus c minus xi I from 1 to c. Naturally, higher values of T indicates presence of an upward trend. Under the null hypothesis, T has a binomial distribution with parameters c and success probability half. Then, as usual, depending on the given level alpha, the test can be constructed. Before we conclude, we note some interesting points. Suppose the observations are non-identical, but each has the same median theta naught under the null hypothesis. Then, sign test statistic has the same binomial distribution with parameters n and half. However, if the observations are dependent, sign test is not distribution free. Using a simple bivariate normal model, this can be observed. Lastly, it can be shown that for Laplace population, sign test gives higher power than the test based on t statistic for small values of n. But we shall discuss all these things while discussing asymptotic relative efficiency. Thus, we have seen that sign test is unbiased, its large sample distribution is normal, and we have found a confidence interval for the location parameter using the acceptance region of sign test. However, in sign test, we have used only the signs of the observations. Therefore, we are losing some information contained in the data. In our next module, we shall show how sign and rank of the observations can be put together to provide another non-parametric test.